Hello friends, welcome back to my YouTube channel Physics Club by Shakti sir. Today I am going to discuss Coulomb's law from the chapter Electrostatics. It is very important topic in our 12th class. So let's discuss its definition and the formula. Then we will discuss few examples so that we can handle the situations when there is any numerical problem. Let's start. So, according to Coulomb's law, from the experiment analysis, he concluded that if there are 2-point charges, so I am drawing these 2-point charges. So, let us say this is Q1 and let us say this is Q2, and from center to center there is a distance r between the two charges, right, and these charges are considered point charges. Okay, point charges. That means the dimensions of the object on which the charge is placed, the dimensions of this particle is very small as compared to the distance between these two particles. Okay, so then we can consider this as the point charges. So we are taking the r from center of one point charge to center of another point charge. So what he stated, according to his analysis, he says that the first statement is the Coulomb force, as these two charges apply force on each other. If they are positive charges, then they will repel each other, and if they are negative charges, still they will repel each other, but if they are of opposite nature, they will attract each other. We know this very well, that if the charges are of opposite nature, there is attraction. So he says that the electrostatic force or the Coulomb force is directly proportional to the product of the charges or magnitude of the product of the charges. And the second statement says this force is inversely proportional to the square of the distance between the charges, that is 1 upon r square. It also says that inverse square law. So when we combine these two statements, we can conclude that the force, or we can say that the magnitude of force, is directly proportional to Q1 Q2 divided by r square. To remove this proportionality, we can write K as a constant of proportionality, Q1 Q2 divided by r square. So this is the very general formula of the Coulomb force, or we can say then the electrostatic force. This is very general result, where K is the constant of proportionality. Okay, let's discuss about K, where K has some specific value, where K is nothing but 9 into 10 raised to power 9 Newton meter square upon Coulomb square. So this is its value in terms of SI unit. Okay, so we need to remember this value to solve the numericals. 9 into 10 raised to power 9, and also K can be equal to 1 upon 4 pi epsilon naught. So this is its value in free space, epsilon naught. So epsilon naught, this 0 as a subscript denotes this value is in the free space, or we can say in air. If the medium between the two charges changes, then its value also changes. Then we will not use 9 into 10 raised to power 9. The value will be different according to the medium between the two charges. But if the medium between the two charges is free space or air, then the value of K is 9 into 10 raised to power 9, and in most of the cases, 99% of the numericals, we will use this value. And otherwise stated, if there is nothing about the medium between the two charges, then by default we will consider it as air. Okay, whereas the value of the epsilon naught is also given 8.85 into 10 raised to power minus 12 Coulomb square per Newton meter square. So this is its value in terms of SI unit. We will keep in mind this value. There are few more properties, very important properties of this Coulomb force, but before going that, we will discuss how we can use this numerical formula in the numericals. So it's very important result, we will keep in mind. Okay, so let's discuss few examples. So the very first basic example is, so example number first, let's say we have this square, okay, and this is 4 Coulomb, this is 4 Coulomb, this is 4q, this is again 4q. These are the charges. This is q1, q2, q3 and q4. Let's say all the sides are equal. Then if there is any charge at the exact center of the square, here let's say the charge here is capital Q, right? So what is the total force acting on this charge? So it's a very basic. By symmetry, Q1 will apply a force in this direction, same force will be applied by Q4 in the opposite direction. Q force will apply in this direction, so the net force will cancel each other. So these two forces will cancel each other. In the same way, the Q3 charge will apply a force, repulsive force on Q, so it will repel Q in this direction, and Q2 charge will repel the charge at the center in this direction. Again these two forces cancel each other, so the net force on the capital Q charge which is placed at the center of the square is 0. Okay, so this is very basic example. So first of all we need to see the symmetry. If there are symmetrical charges placed, then there may be the possibility that the net force on the symmetrical charge is 0. But if any, in this example, any of the charge has some different value, then the net force will be something else. Let's see. So example number 2, let's see, we have this charge. Again I am drawing this spherical system. So these are the sides of the square. Okay, L, each side L. Let's say again Q1 equals to 2 Coulomb, Q2 equals to 2 Coulomb, Q3 equals to 1 Coulomb, and here Q4 equals to 2 Coulomb. In this situation, if there is any charge at the center of this square, then what is the net force acting on this charge which is placed exactly at the center C? Let's say this is Q. So what is the net force acting? So from the symmetry of this diagram we can say that the forces applied by Q2 and Q4 will cancel each other due to the direction, as one force will be in this direction, another force will be in this direction. So these forces cancel each other due to symmetry, and they have equal charges and equal distance between the Q2 and C. But the charges at Q1 and Q3, they are of opposite, they are of not same magnitude. That's why the force acting on the charge placed at center will not cancel each other, as Q1 act on Q in this direction. So let's say this force is F1, and the force due to Q3 is in this direction. Let's say this is F3, but the magnitude of F1 and F3 are not equal because this is 1 coulomb and this is 2 coulomb. Let's say what can be the value. Let's say this is A, B and C at center, this is D and this is E. Okay, so what is the distance between A and C? By Pythagoras theorem we can say AD is equal to under root of L square plus L square. So the AD is nothing but under root 2 L AD, and AC is half of AD. This comes out to be this. So this is AC, and it is also equal to DC. So AC and DC both have L by root 2 distance. Okay, so what is the value of F1? F1 is equal to K Q1 Q divided by AC square. It is equal to K Q1 equals to 2 coulomb, this is Q, and AC equals to L by root 2 square. It is along AD direction, right? A to D, or we can say C to D direction, F1. So in the same way, F3 can be written as K 1 coulomb Q upon CD square. It is K Q divided by L upon root 2 square. So this is along C to A and this is along C to D. Keep in mind, it means that F1 and F3 has opposite directions but their magnitude are not same. So what is the net force on Q? So the net force, so which has the higher bigger magnitude? F1 has larger magnitude as compared to F3. So it means that the net force will be F1 minus F3. This is the net force. So F1 is nothing but 2kq divided by L upon root 2 square minus kq divided by L upon root 2 square. Let's solve this. It comes out to be 2kq minus kq. It is kq upon L upon root 2, something like this. So further we solve it, it comes out to be 2kq divided by L square. So this is the net force acting on the charged particle placed at the center of the square, and it is directed, this force is in Newton and it is directed along CD. So this is our answer. Okay, so let's discuss one more example. So example number 3. So let's say in the example number 3 we have a situation something like this. It says that, let's say we have these two big objects having some charge distribution. So there is symmetrical charge distribution, positive symmetrical charge distribution. Okay, and here radius is r, and one more object, again there is some symmetrical charge distribution on the sphere. So we have two objects, again its radius, let's say r. Okay, so the question arises is, if these two spheres bring close to each other, something like this, if these two spheres bring close to each other like this, so what will happen? Can we apply the Coulomb's law formula here or not? Let's see. When we bring these two spheres close to each other, the symmetrical distribution as shown in figure 1 and this is figure 2. In figure 1, both the spheres has a symmetrical distribution of charge, but when these two spheres bring close to each other, the distribution of charge does not remain symmetrical. So the charge becomes unsymmetrical as shown in the diagram. So this is the distance, this r, and this is also r. As the charge distribution on the spheres become unsymmetrical, so we cannot apply the Coulomb's law on these in this situation, because Coulomb law is applicable only for the point charge objects. So I am writing this: Coulomb law is applicable only for point charges which must be at rest. Okay, so these are not considered as the point charges. In figure 1, these spheres can be considered as point charges under the condition that all the total charge is concentrated at the center. Similarly, here all the charge can be considered to be situated at the center, and this statement, we can consider this statement that all the charge on the body can be considered to be situated at the center if the charge is symmetrical on the object. So here the charge is symmetrical, therefore, so in this diagram the charge is symmetrical, therefore we can say that the total charge can be considered at rest. Okay. But in figure 2, the charge is unsymmetrical, so we cannot say that the total charge can be considered to be situated at the center C1. Okay, at the center C1, and same the total charge, let's say Q2, here Q1, we cannot consider total charge Q2 to be situated at the center C2 because of the unsymmetry of the charges on the surface of the sphere. Okay, so as these charges are unsymmetrical, so we cannot apply Coulomb's law. Okay, keep in mind this situation. All right, let's move towards the another example. So example number 4. Example number 4 says, let's say we have two charges, two free charges, this one and another one somewhere here. This has magnitude q and the second charge has magnitude 4q. This is first charge, this is second charge. Okay, and both are positive in nature. They are placed at a distance of L. The distance between them is L. कहता है under what situation a third charge to be placed so that the entire system is in equilibrium. So where should the third charge to be placed so that the entire system is in equilibrium. Okay, so we will discuss this numerical. This is very important numerical. So firstly we will discuss what is equilibrium in the electrostatics. So equilibrium in electrostatics is if a system is in equilibrium, it means that the net force on each charge should be 0. The resultant force on each charge should be 0, then only the system will be in equilibrium. As in this example we have two charges, it means that this is a two charge system. So in this system we have two charges having magnitude q and 4q. So this system is in equilibrium if the net force on charge 1, that is plus q, is 0, as well as the total force acting on second charge that has magnitude plus 4q should be 0. How is this possible? As there are only two positive charges, so that there must be repulsion between them. Okay, as they have same nature, so there is a repulsive force acting between these two charges. So in this diagram we cannot say that the system is in equilibrium. So what we need to do so that the system will be in equilibrium? So to make this system in equilibrium, we will consider a third charge and place that third charge near the charge having smaller magnitude. So here first charge that has magnitude q has smaller magnitude, so we will place this third charge capital Q near the charge having smaller magnitude. All right. Okay, let's say the distance between this is x, so this becomes L by x. So this distance become L by x. Again, what should be the nature of this third charge? Let's see. Let's discuss the nature of this third charge. This third charge must be negative in nature. Why negative in nature? Let's consider if it is positive, then what will happen? If it is positive, then this 4k charge apply a force on q in this direction. Okay. So this force is 1 due to 2, 1 due to 2 in this direction towards left, and again the force due to capital Q charge that must be repulsive if it is positive, then again this is the force on 1 due to third. As both the forces acting towards left, so the net force on the first charge cannot be 0. So this charge is not in equilibrium. Okay, but if we consider the third charge is negative in nature, let's see what happens. Now the force due to second on first, this is force due to second on first, so first due to second in this direction. Okay, but the force due to the negative charge, that is the third charge on first, is in this direction. It's force on first due to 3. Now we can see that F12 and force 13 having opposite directions. So there are chances that the first charge can be in equilibrium if these forces become equal in magnitude. So for equilibrium of the third charge, what we can say, the total force acting on first charge should be 0. Okay. So before solving such situations, firstly we need to calculate where should the charge q should be placed, that is we need to find the value of x. What should be the value of x? So to find the value of x, how we can find the value of x? As third charge should also be in equilibrium, so the net force acting on q must be like this, that is this is the force on 3 due to 2 and this is the force on 3 due to 1. They must be of opposite nature. Okay, no, as the third charge is negative, this is negative, okay, this is negative in nature, therefore the here you can see, therefore the second charge apply attractive force on the third charge. So we can say this is the force on third due to second, attractive force. Similarly, there is force on third due to first, attractive force. Okay, so these two forces should be equal, then only third charge is in equilibrium. So according to the diagram, there is one charge, this is q, and there is some another charge having magnitude 4 q, this is x, this is l minus x, according to the above this diagram. Okay, so their magnitude must be equal, something like this. So what we can write? We can write it as k q q divided by x square is equals to k 4q q, capital Q, divided by L minus x square. Here we can solve this k, this q cancel, capital Q will remain cancel. So the next step can be 1 upon x square equals to 4 upon L minus x square, something like this. So from here we need to calculate the value of x. So it is 1 upon 4 equals to x upon L minus x whole square. So this is 1 upon 2 equals to x upon L minus x. Now we can solve this. 1 upon 2 L minus x equals to x. So L minus x equals to 2x. So L equals to 3x. So x is equal to L by. So we calculated the value of x. Okay. Now for the equilibrium of charge 1 that has magnitude q, we need to apply this force magnitude and this force magnitude, that is magnitude of force 1 2 and magnitude of force 1 3 should be equal. Let's solve. For the magnitude of for the equilibrium of charge q. So the forces on charge 1 due to 3 must be equal the force on 1 due to 2. Okay, so this is k q divided by x square, because the distance between 1 and 3, here you can see the distance between 1 and 3, this one, this distance is x, but the distance between 1 and 2 is L. Okay, so here k q 4q divided by L square. Let's solve this. K cancel each other, this term cancel each other. Okay, so the value of x is L by 3, we will use this value. So q upon L by 3 square equals to 4q upon L square. So this comes out to be 9q divided by L square equals to 4q divided by L square. Okay, so these terms cancel each other. So further, the capital Q is nothing but 4 by 9 of small q, 4 by 9 of small q. So this is its magnitude. But we have conceptually calculated that the nature of this capital Q is must be negative. Nature must be negative. Therefore, the capital Q can be written as minus 4 by 9 of small q. So this is a very important numerical. You need to calculate the value of x and then the value of third charge particle which you are going to place between the two charges, so that the system will be in equilibrium. In this way we can solve this numerical and says that if the third charge particle, which has magnitude minus 4 by 9 of small q, is placed at a distance of L by 3 from the first charge, then the whole system will be in equilibrium. I hope you will enjoy this lecture, you understand this lecture, and stay tuned for my next videos. Wish you all the best. Bye bye.